Hello, welcome. In this short video, let us look at an example illustrating how to verify whether a statistic is a sufficient statistic for estimation of a parameter in a model. Specifically, we will look at the conditional distribution of the data given the statistic and see if it is independent of the parameter. So given the following linear model, x of n is equal to a plus w of n, where n is equal to 0 to n minus 1, we know that the minimum variance unbiased estimator for the parameter a is given by a hat is equal to 1 by n into the sum n equal to 0 to n minus 1 x of n, which is clearly the sample mean. Now we can see that the estimator a hat can be defined by the statistic t of x, where t of x is equal to the sum of the n observations, n equal to 0 to n minus 1 x of n. So now the problem is we want to verify whether the statistic t of x is sufficient for estimation of the parameter a. So formally this can be done by looking at the conditional distribution of x given the statistic t of x is t of x equal to t naught, and it can be a function of a or not. So we want to look at this conditional distribution defined as the ratio of the distribution of x comma t of x equal to t naught with the parameter a over the distribution of t of x, that is the marginal distribution of t of x equal to t naught as a function of a. So if this ratio is independent of a, that means if this is not a function of the parameter a, if it is not a function of parameter a, then clearly the statistic t of x is a sufficient statistic. So now our goal is to basically calculate the conditional distribution of x given t of x equal to t naught. Let us look at the numerator first. It is probability distribution of x, the joint distribution of x, and t of x equal to t naught, the parameter a, which is clearly equal to the product of distribution of x multiplied by the delta function at t of x minus t naught. So, and since probability distribution of x with the parameter a is assumed to be a Gaussian distribution, then we have 1 by 2 pi into sigma square over n by 2 multiplied by exponential of minus 1 by 2 summation n equal to 0 to n minus 1 x of n minus a whole square divided by sigma square multiplied by the delta function at t of x minus t naught. Now by expanding the exponent of this function, we have exponential of minus 1 by 2 sigma square sum n equal to 0 to n minus 1 x square of n, plus we have a times the sum n equal to 0 to n minus 1 x of n divided by sigma square. Since we have a 2ab term here, the 2 will cancel with the 2 in the denominator. And then the last term is clearly equal to a square divided by sigma square multiplied by 1 by 2. Of course, it is repeated n times, so we have minus n a square over 2 sigma square. And then we have the delta function t of x minus t naught. Now we can rewrite the function as follows: 1 by 2 pi sigma square power n by 2 exponential of the term 1 by 2 sigma square multiplied by the sum of the squares n equal to 0 to n minus 1 x square of n, and the sum n equal to 0 to n minus 1 x of n is clearly the statistic t of x. So this can be rewritten as a times t of x over sigma square. but when you use the function delta of t of x minus t naught, that is, you basically shift the value t of x to t naught. That means we have plus a times t naught over sigma square minus n into a square over 2 sigma square. So this is the numerator for the conditional distribution of x given the statistic t of x is equal to t naught. Now the denominator, that is the marginal distribution of t of x equal to t naught, the parameter a, can be defined as follows. Since t of x is equal to the sum n equal to 0 to n minus 1 x of n, and since t of x is the sum of basically the observations, it should have the same distribution as the observations, that is its mean, that is expectation of t of x is equal to n times the expectation of the observation x of n, which is a. So its expectation is n into a. Similarly, the variance of t of x should be equal to n square times the variance of the estimator a hat, which we know to be sigma square by n. Therefore, the variance of t of x should be n times sigma square. So by using these two moments, we can clearly say that the probability distribution of t of x equal to t naught, the parameter a, is a Gaussian distribution, which is defined as square root of 2 pi into n sigma square multiplied by exponential of minus 1 by 2 times n into sigma square multiplied by t of x minus n into a whole square. And since we are looking at the value t naught, this should be multiplied by delta of t of x minus t naught. So clearly this is equal to 1 by square root of 2 pi n sigma square exponential of minus 1 by 2n sigma square multiplied by t naught minus n a whole square. Now the conditional distribution can be written as follows, that is probability of x given t of x equal to t naught, a function of a or not so. So the numerator is given by this result, which is equal to 1 by 2 pi sigma square over n by 2 multiplied by exponential of, the first term is 1 by 2 sigma square, the sum n equal to 0 to n minus 1 x square of n, that is the sum of the squares. And the next two terms are a times t naught by sigma square, that is a plus a t naught by sigma square minus n a square over 2 sigma square minus n a square over 2 times sigma square. And the denominator is given by this distribution. It is divided by 1 by 2 pi n sigma square over 1 by 2 exponential of, the first term is clearly equal to t naught square over 2n sigma square, and the second term is equal to plus 2 times t naught multiplied by n into a over 2 times n into sigma square. The third term is clearly equal to minus n square a square over 2 times n into sigma square. Clearly these two terms cancel with these two terms, and therefore the function, that is the conditional distribution of x given t of x equal to t naught, is clearly independent of the parameter a, and therefore this is independent of a. Therefore t of x is a sufficient statistic. Thanks for watching.